Phasors and refraction. To explain refraction in terms of phasors, I'm going to start with a seaside scene. We have a person in distress in the water and a lifeguard on the beach. The lifeguard could take the most direct route to the person, but they know that they can travel more quickly on the sand than in the water, and so they could take this route, where they have the maximum distance on the sand and the minimum distance in the water. They could, at the other extreme, take this route, where they have the minimum distance on the sand and the maximum distance in the water. This route would clearly take longer than either of the other two routes. The fastest route would be a compromise between the shortest route and the route with the least distance in the water. Something like this. Of course, they could take any number of other routes, but I'll highlight this fastest route. Let's move now to a situation with light travelling from a source through air, where it travels faster, then through glass, where it travels slower, to reach a detector. I've marked on some of the possible routes that the photons could take. This route has the greatest distance and also the greatest distance through glass. The next route is significantly shorter with a lot less glass to travel through, and so this will be much quicker, meaning the phasors from these two routes will not be anywhere near aligned. Moving on, we still have significant drops in travel times. The fastest paths, and those very close to it, will have the closest travel times. That would be these three paths and those in between. This is where the phasors will be more closely aligned. I'm now going to plot the direction of the phasors for those 11 possible routes. First, the fastest route. If we say the phasor is pointing in this direction, the phasors either side of it will have turned a little bit further round anti-clockwise, as they've been travelling for a little bit longer, so they might be aligned like this. If I add in all the other phasors, we'd get something like this, and the resultant phasor would go from the back here to the front. If I just consider the fastest route phasor and those either side of it, which I'll reproduce over here, you'll see that we have just about the same resultant phasor. The probability of photons arriving is directly proportional to the square of the resultant phasor. So the fastest route contributes the most to the probability of photons arriving. This matches up with what you would have learned previously about refraction, that as light travels from air into glass, it bends towards the normal. Let's look at how lenses can be explained using phasors. Here we have a source of light, a lens, and a detector. Some of the possible routes for the photons travelling from the source to the detector would be these. The central route here, the straight through route, has the shortest distance, but has the greatest thickness of glass to travel through, and the light travels more slowly through the glass, although the photons will still rotate at the same speed. The outer routes are longer but have less glass to travel through. I'll just run through that again. The middle paths are less overall distance but with more glass, where the photons travel more slowly, but the frequency and therefore the rotation speed of the phasors is unchanged. The outer paths are longer but with less time in the glass. The overall effect is that all the paths take the same amount of time, and so the phasors from all the paths are aligned. So the 7 phasors from those 7 routes might be aligned like this, giving this as a resultant phasor. So a lens leads to a high probability of the photons being detected at the focus. This produces a bright region, as we know.